So in this part of the video, I'm going to basically give you a review of some of the basic properties of the scattering matrix. So first, let's talk about reciprocity. If a network is indeed reciprocal, that means that you can interchange source and load and essentially get the same results. That is given as basically SNM is equal to SMN, as long as N and M are not the same. So a classic case for a two-port network, for example, is that the S12 and the S21 are basically the same. So the S21 for the network, meaning the power you get in port 2 when you feed it from port 1, or vice versa, is basically going to be equal the same numbers. That's a classic case in all passive networks, but it does not happen, for example, when you have an amplifier. Because if I do have an amplifier, the power is amplified this way and not the other way around. So in a typical amplifier, S21 won't be equal to S12. The other interesting property is symmetry. So a network may or may not be symmetric. If a network is symmetric, then the S11 will be equal to S22 or S23 and so on. But if it's not symmetric, it won't be the case. A classic case of a symmetric network is, for example, this. So if I just have a network that simply has a series element, let's say some type of an impedance Z, then clearly this is a symmetric network, and S11 will be equal to S22. On the other hand, this network here is not symmetric. It's actually reciprocal, clearly, and so that means that S12 will be equal to S21, but here S11 won't be equal to S22 because the network does not look the same if you look at it this way or if you look at it this way. So be careful. That's why the N different than M condition is actually placed there, is because not all reciprocal networks are actually symmetric. Perhaps more interesting is the lossless part. In the lossless part, it means that the network itself does not consume any power. For example, in this case here, if my Z is actually equal to Jx, it means that the network itself won't consume any real power. And so that means that the total amount of input power will equal to the total amount of output power. And I do know how to calculate those. All the incident waves will basically give me my input power, and all the reflected waves will basically give me my output power. So if I make those two quantities the same, then I can basically use matrix algebra to write that AK square will be given as A complex transpose, conjugate transpose. This is what this thing T means. And then that will be equal to B conjugate transpose times B. Conjugate transpose means you take the columns, you make them into rows, and you basically take the complex conjugate of all the numbers of the matrix. So if you just do a simple matrix algebra, you basically come up with this very famous equation that actually must be satisfied for any network that is lossless. For those of you who might have taken any type of quantum mechanics, you've seen this equation before, and that basically characterizes a unitary matrix. Usually in quantum mechanics, you'll use the dagger to actually replace that little t that you see there. They have very, very important implications in there too. But nevertheless, let's write this thing in slightly more detail. So S transpose complex times S will basically make the unit matrix, which is given right here. And if I actually do this multiplication, I will get some equations that I really want to show you in a little bit more detail. For example, the first equation that you will see right here simply says that S11 square plus S21 square plus S31 square plus all the way to Sn1 square should be equal to 0. And so essentially that means that if you feed this network from port number 1, which is basically given the wave A1, that power must exit from all the other ports. So S21 square is nothing else but B2 over A1 square. S31 square is nothing else but B3 over A1 square, magnitude, and so on and so forth. And so, of course, S11 square will be the reflection in that same port. So that simple equation is very intuitive. If you feed the network from port 1, that power will either be reflected into port 1 or will go and exit from one of the other ports. So when you sum all of these numbers up, you must get equal to 1. If this guy is actually less than 1, this network actually is lossy. It means some of the power did not make it out. It was actually consumed in the network. The same equation is actually written here. Essentially, the easiest way to remember these equations is to basically take the S matrix. This is the S matrix right here. And just remember that you basically sum the column square. So the first column square must be equal to 1. The second column square must be equal to 1. The nth column square must be equal to 1. Right? So this is the case when you feed this from port 1, you feed this from port 2, you feed this from port n. And then there is another equation you can remember, which is actually given right here. This basically says that if I consider those columns as vectors and I multiply them, I will basically get equal to 0. Where, as we're going to see in a little bit in the example, where this thing actually becomes interesting is you can use this equation to actually find some of the matrix elements. For example, for a two-port network, this equation means that S11 square plus S21 square is equal to 1. And so that means that if I do know the S11, I can actually find the S21 at least magnitude-wise. And sometimes by using a little bit more knowledge of the network, I can also find the phase of S21. Questions of the three basic properties of the S matrix.
So I didn't quite get, so what's the reasoning again? Could you say that again for why if you take two different columns and you're looking at the conjugate of one column, you're going to get 0?
Yes, I did not actually give a physical reasoning for that. I simply said that this is also a property following this STS is equal to I. I didn't really give any physical reasoning for that. The physical reasoning, at least in my mind, is right here.
Okay, great. Because if it all has to
That's right.
stay, then...
That's right. Any other questions? All right. So in this part, I'm going to show you an interesting example of calculating the S matrix of a network utilizing the basic properties that we just saw. So this is a very interesting, it's an electrically small impedance step, which essentially means that you come from one impedance Z01 and you exit from a different impedance Z02. So if this was a microstrip line, for example, you would see two different widths, one following the other. And that type of an impedance step is used a lot. One example is the project that you are doing. So electrically small means that each one of these lines basically has an electrical length that is practically 0. So that means that we will assume that there is no phase shift between the input and the output. The wave basically does not gain any phase or lose any phase here because the electrical length is practically 0. So let's start. Let's calculate S11. So again, S11 basically means terminate port 2 to its characteristic impedance. In that case, means terminate it to Z02. And then look at the reflection coefficient from port 1. So this is pretty easy to do. You just now see that port 1 is loaded with an impedance that is equal to port to Z02. And so that means that S11 will be equal to Z02 minus Z01 over Z02 plus Z01. Now let's calculate S21. You can do the calculation of S21 as you've seen in a previous video just by looking at the voltages, meaning V1 and V2. And I do invite you to actually do that. You will learn quite a bit. But instead of that, here we can use the fact that this is an electrically small impedance step. That means it's necessarily a lossless network, assuming ideal transmission lines. And that means I'm going to use this property here to calculate my S21, since S11 is known. So by using this property, I can basically get that the S21 will be equal to plus or minus square root of 1 minus S11 square. And so now I have to basically make a choice. Do I pick the plus sign or the negative sign? Because this is an electrically small network, and that means there should be no type of a phase shift, I must pick the plus sign here. If I were picking basically the negative sign, I would have implied that there was basically 180 degrees phase shift, which actually nothing here can actually give you 180 degrees phase shift because there is no electrical length. And so from this very simple two-step argument, I now know my S21. And because my network is reciprocal, the S12 will actually be equal to the S21. So now I'm using actually the second property of the matrix that this is reciprocal, the first being I use the lossless part. Now finally I have to do the S22, and what I hope you will avoid here is the temptation to say that S22 is equal to S11, as it has actually been the case in the other examples we have seen. That is not true because the network here is not symmetric. It does not look the same when you look at it from port 1 and you look at it from port 2. So you have to be careful here. S22 must be calculated by the definition, which basically means, again, you have to look at the reflection coefficient here when port 1 is terminated with its own characteristic impedance. And so now port 2 will basically see a load that will equal Z01. And so that means that the S22 will be equal to Z01 minus Z02 over Z01 plus Z02, which actually will make the S22 to be equal to negative S11. And so now my full matrix will actually be given by this equation right here, where the S11 was the number I basically wrote before, Z02 minus Z01 over Z02 plus Z01. So it's a very quick calculation, but you can do the same type of argument for many, many networks that are lossless and reciprocal and perhaps symmetric. In our case, it was not.